Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a very gentle but profound idea, one that quietly reshapes how modern physics understands reality itself. We'll be exploring quantum fields, not as a technical theory filled with symbols and equations, but as a calm, intuitive picture of the universe, one where space is never truly empty, and where what we call particles are more like ripples in something deeper and ever-present. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable, and when you're ready, feel free to leave a comment letting me know where in the world you're listening from and what time it is for you right now. It's always a small kind of magic to see how these slow conversations stretch across nights, time zones and different corners of the planet. Now you might want to dim the lights a little, maybe let a fan hum softly in the background, or just notice the steady rhythm of your breathing. And if your mind begins to wander as we go along, that's perfectly fine. Let it drift. We'll still be here, gently unfolding the story. Tonight we won't be rushing toward answers. Instead, we'll slowly adjust a picture, one you've probably carried with you since school, about what the universe is made of. And with that, we can begin. Most of us, without ever being formally taught, grow up carrying a very specific image of reality. It's a picture that feels simple, solid, and reassuring. The world, we're told, is made of things: tables, stones, trees, stars, and eventually atoms. And those atoms, in turn, are made of even smaller things. Little particles, tiny hard bits of matter, moving around like microscopic beads. In this picture, everything feels comfortably object-based. Matter is something you can point to, even if you need a powerful microscope to do it. An electron becomes a minuscule dot. A proton becomes a slightly heavier dot. Space is imagined as a kind of empty stage where these dots move around, collide, stick together, or drift apart. Nothing is happening in the empty regions in between. They're just empty. This way of imagining the universe isn't silly or naive. In fact, it works extremely well for everyday life. When you roll a ball across the floor, it behaves like an object. When you stack books on a table, they stay put. Even when scientists first discovered atoms, thinking of them as tiny solid pieces helped make sense of chemistry, materials, and much of classical physics. It's a picture that helped humanity build bridges, engines, and eventually spacecraft. So if you've always imagined reality as being made from countless tiny building blocks, you're in very good company. Your intuition didn't fail you. It simply grew up in a world where this picture was good enough. But physics has a habit of gently tugging at the edges of our favourite ideas. As experiments became more precise, and as scientists began to look more closely at the smaller scales of nature, this solid, particle-based picture started to feel strained. Not broken in a dramatic way, just slightly uncomfortable, like a shoe that fits well enough until you walk a little farther than usual. Light, for instance, refused to behave like a simple stream of particles. Sometimes it acted like a wave, spreading out, interfering with itself, creating delicate patterns of brightness and darkness. Other times, it arrived in tiny, discrete taps of energy, as if it really were made of individual packets. Trying to force light into being only one thing or the other began to feel like asking a melody to be only a note or only a rhythm, but never both. Electrons too resisted being pinned down as tiny dots. When scientists tried to track exactly where an electron was, it didn't sit patiently in one place. Instead, it behaved more like a blur, a smudge of possibility. The harder one tried to say, "You are exactly here," the less certain everything became, and then there was empty space itself. that quiet background we imagined as a blank stage. The deeper physics looked, the less empty it seemed. Even when all visible matter was removed, experiments hinted that something subtle remained: activity without objects, presence without particles. None of this arrived as a sudden declaration that everything we knew was wrong. Physics rarely works that way. Instead, it arrived as a series of small, persistent nudges. Gentle reminders that the universe might not be built from tiny solid pieces after all. At this point, it would have been tempting to replace one rigid picture with another equally rigid one. To simply say, fine, particles are strange dots that behave oddly, and move on. But modern physics took a different path, a quieter, deeper one. Rather than asking, what are particles made of? It began to ask, what if particles aren't the foundation at all? This question doesn't demand that we throw away our intuition. It asks us to soften it, to imagine that the dots we've been focusing on might be more like signs, or footprints, or ripples, evidence of something else underneath. Think for a moment about waves on the surface of a lake. If you didn't know about water, you might think the ripples themselves were objects, little moving ridges that appear, travel, and disappear. But once you understand the lake, the ripples stop being things in their own right. They become movements of something deeper, something that is always there, whether the surface is calm or disturbed. Modern physics suggests that particles may be like that. Not tiny solid beads floating in empty space, but brief patterns of motion in something far more continuous and far more subtle. This idea doesn't remove reality, it deepens it. It replaces a universe made of scattered bits with one made of quiet backgrounds and gentle activity. And while that may sound abstract, it turns out to be one of the most successful ways we've ever found to describe nature. For now, you don't need to hold on to definitions or remember terminology. It's enough to notice the shift in mood. We're moving from a world of objects to a world of underlying presence, from things sitting in space to something filling space, everywhere, all at once. As this idea settles in, there's no need to rush. Like adjusting your eyes in a dim room, it takes a moment for a new picture to come into focus, and in the calm that follows, we can begin to meet the central character of our story. Not a particle, but something quieter and far more patient. A field. And with that thought gently resting in the background, we can let the old picture loosen its grip just a little and allow a deeper one to slowly take its place. As that familiar picture of a particle-built universe begins to loosen, it helps to notice where it first starts to feel uncomfortable. Not shattered, not wrong, just stretched. Like a story that still mostly works but requires a few too many exceptions to keep going smoothly. For a long time, the idea that everything is made of tiny solid pieces served physics beautifully. It explained why objects feel solid, why materials have structure, and why things bounce, break, or stick together. Even atoms, once imagined as indivisible, were eventually revealed to have internal parts, and the story continued. Smaller pieces, arranged in clever ways, building larger ones, a satisfying hierarchy of little building blocks. But as scientists learned to probe nature more delicately, this picture began to show subtle cracks. Light was one of the first troublemakers. If light were truly just a stream of tiny particles, it should behave like a spray of microscopic pellets. Each one should travel in a straight line, hit a surface, and stop. Yet when light passed through narrow openings, it spread out. When two beams met, they didn't simply cross paths, they interfered. Bright and dark bands appeared, as if light were rippling, overlapping, cancelling itself out in places and reinforcing itself in others. This wasn't the behaviour of neat, independent objects. It was the behavior of waves. And yet, when scientists tried to explain other experiments using only waves, light resisted again. It arrived in discrete taps of energy, never in smooth dribbles. Each interaction came as a tiny packet, a single click rather than a continuous flow. Light seemed to insist on being both spread out and indivisible, both smooth and step-like. Trying to force it into the role of a tiny solid object began to feel less like explanation and more like compromise. Electrons were even more unsettling. In early atomic models, electrons were pictured as miniature planets, orbiting a nucleus, tracing tidy paths through space. This image was comforting, familiar. It borrowed directly from the motion of moons and planets we already understood, but when experiments tried to confirm these orbits, electrons refused to cooperate. Instead of following clear paths, electrons behaved as if they were smeared out, not lost, not vague, just distributed. When physicists tried to say exactly where an electron was, the answer came back as a region, a cloud of likelihood rather than a point. The harder they pressed for precision, the less definite the picture became. It wasn't that electrons were hiding their position out of spite. It was that the idea of a tiny dot moving along a precise track no longer fit what nature was doing. And then there was empty space. In the particle picture, empty space is nothing more than the gap between objects, a silent stage where things happen, but which itself does nothing at all. Remove all the particles and you're left with absolute nothingness. But experiments began to suggest that even when every detectable particle was removed, space itself was still quietly active. Tiny fluctuations appeared, gentle tremors that had no obvious source. Energy seemed to flicker in and out, not as something created from nothing, but as something that never fully disappeared in the first place. This was deeply unsettling for an object-based worldview. If particles were the only things that existed, then nothing should truly mean nothing. And yet, the universe seemed unwilling to give us emptiness that was completely still. None of these discoveries arrived like thunderclaps. There was no single experiment that shouted, "The particle picture is wrong." Instead, there was a growing sense of awkwardness, a feeling that the rules had become too complicated, too patched together, too dependent on special cases and exceptions. Particles sometimes acted like waves. Waves sometimes arrived like particles. Objects refused to sit neatly in space. Empty space refused to stay empty. It was as if reality were gently suggesting that we were asking the wrong question. Rather than asking how particles behave so strangely, modern physics began to ask something quieter and more revealing. What if particles are not the main actors at all? What if they are not the fundamental things we imagined them to be? This shift is subtle, but profound. Imagine watching the surface of the ocean during a storm. Waves rise, travel, collide, and disappear. If you focused only on the waves, you might catalogue them. Measure their heights, track their paths, you might even give them names. But eventually you would notice something important. The waves are not separate objects, they're movements of the water itself. When a wave passes, nothing permanent has travelled across the ocean. The water is still there. The wave is a pattern, a temporary organisation of motion, not a thing that exists independently. Physics began to wonder if particles might be similar. Not independent beads drifting through emptiness, but localized patterns of activity in something deeper and more continuous. This way of thinking does not deny the reality of particles. We still detect electrons. We still see light arrive in tiny packets. We still build technology that relies on these behaviors, but it reframes what those detections mean. Instead of revealing tiny solid objects, they may be revealing moments when an underlying structure briefly announces itself. This reframing also explains why particles behave so consistently. Every electron in the universe has exactly the same properties. Not almost the same, not statistically similar, precisely the same. In a particle as object picture, this is strangely miraculous. Why would countless separate objects be perfect copies of one another? But if electrons are patterns in a deeper background, their sameness becomes natural. Like waves on the same ocean, they share the same medium, the same rules, the same possibilities. Slowly, gently, physics began to trade a universe of things for a universe of behaviors. A universe not built from tiny bricks, but from ongoing activity, from something that exists everywhere, even when nothing seems to be happening. This doesn't make reality less real. If anything, it makes it richer. It replaces a sparse landscape of isolated objects with a continuous, quiet presence underlying everything we see. At this stage, there's no need to define that presence precisely. No need for formal language or technical labels. It's enough to notice the direction of the shift. We're moving away from asking where the pieces are and toward asking what is always there, even when no pieces appear. The particle picture doesn't collapse here, it gently steps aside, making room for a deeper idea to enter the story. An idea that explains waves and particles, sameness and uncertainty, presence and emptiness, all with a single, unifying background. And as we allow that idea to settle in, the universe begins to feel less like a box of objects and more like a continuous fabric, quietly capable of motion, a fabric we're just beginning to notice. Once the particle picture begins to feel strained, there is a quiet moment that follows, not a moment of confusion, but one of openness. It's the pause that comes when you realise you don't actually need to force the old idea to work anymore. You're allowed to set it down gently, without replacing it right away. Physics reached that pause too. Instead of asking how particles could behave in so many contradictory ways, scientists began to ask a softer, more patient question. A question that didn't demand immediate answers or sharp definitions. What if particles are not the deepest layer of reality? What if they are not the foundation, but the surface expression of something more subtle? This question doesn't sound dramatic, it doesn't overthrow the world overnight, but it changes the direction of everything that follows. When we grow up, we learn to think of things as the most basic units of existence. A chair is a thing, a stone is a thing, even a grain of sand feels like a thing in its own right. So it feels natural to assume that if we keep breaking matter down, we'll eventually arrive at the smallest possible thing, a final, indivisible object, a kind of ultimate dot. But nature has been quietly suggesting that this expectation may come from our habits, not from reality itself. Think again about the ripples on a lake. If you had never seen water before, you might point to a ripple and say, "That is something," and in a sense, you wouldn't be wrong. The ripple is real. It has a shape, a speed, a direction. You can see it. You can measure it. But the ripple is not independent. It does not exist on its own. It depends entirely on the lake beneath it. Now imagine asking, what is the ripple made of? You could describe its height, its curvature, its movement. But eventually the most honest answer would be, it is made of the lake, moving in a particular way. This is the spirit of the question modern physics began to explore. What if an electron is not a tiny bead moving through space, but a way that something deeper is moving? What if a photon is not a little particle flying from place to place, but a brief, structured disturbance in an underlying background that is always present? In this picture, particles don't disappear. They simply change their role. They stop being the bricks of reality and become its gestures, its moments of emphasis, its localized events. This shift is subtle, but it has an important emotional effect. It removes the pressure to imagine invisible dots behaving like familiar objects. You no longer need to picture an electron as a microscopic marble or light as a stream of glowing pellets. Instead, you can allow yourself to think in terms of patterns, motions, and activities. This also explains why particles can be so strange without being inconsistent. A ripple can spread out and still arrive in distinct peaks. A vibration can be distributed across a surface and still transfer energy in discrete taps. These behaviors feel odd only if we insist on treating them as properties of solid objects. Seen as patterns, they begin to feel natural. There is another quiet advantage to this way of thinking. It softens our relationship with uncertainty. In the particle picture, uncertainty feels like ignorance, as if the particle really is somewhere specific, doing something definite, and we simply fail to know it precisely. But when particles are understood as patterns in something deeper, uncertainty becomes part of the description itself. It's not a flaw. It's a feature. A ripple does not have a single exact location. It has a region where it is most noticeable, and gentle tails where it fades away. Trying to pin it down to one point misses the nature of what it is. This idea allows physics to describe reality without pretending it is simpler than it actually is, and importantly for us, it allows us to listen without needing to solve anything. At this stage in our journey, it's important not to rush ahead and name the underlying structure too quickly. Names have a way of hardening ideas before we've had time to feel them. Instead, it's enough to sit with the notion that something continuous and ever-present may underlie everything we observe. Something that exists even when nothing seems to be happening. Something that does not switch on and off with the appearance of particles. Something that fills space so completely that space itself may simply be the way we experience its presence. This way of thinking also reshapes how we imagine emptiness. In an object-based universe, emptiness is the absence of things. But in a universe built on underlying presence, emptiness becomes a kind of calm, a resting state, a moment when nothing is being emphasized, but everything is still there. Like a quiet room that hasn't lost its air, or a silent instrument that hasn't lost its strings. This reframing invites patience. You don't need to hold the entire picture at once. You don't need to get it in a flash of insight. The idea works even if it stays a little blurry. In fact, it works better that way. Because what physics is offering here is not a new object to imagine, but a new attitude toward what it means to exist. An invitation to see reality not as a collection of static pieces, but as something more like a continuous, responsive background, capable of motion, pattern, and rest. Soon we will give this background a name, a simple word, already familiar but about to take on a deeper meaning. And once that word enters the story, many of the puzzles that trouble the particle picture will begin to feel less like problems and more like natural consequences. For now, it's enough to notice that the universe may not be built from things sitting in space, but from something always there, quietly capable of becoming things when the moment calls for it. And as this softer question settles in, it prepares the ground for meeting the true protagonist of our story. Not a particle, not an object, but a presence that has been with us all along. After letting that softer question settle, the story is finally ready for a word that has been quietly waiting in the background. It's a word that sounds technical at first, but turns out to be surprisingly gentle once you spend a little time with it. That word is field. In everyday language, a field often means an open space, a meadow, a place where things grow. But in physics, the word has a different, more abstract meaning. A field is not a place, It's not a thing you can point to or pick up. Instead, a field is something that has a value everywhere. That sentence may sound a bit stiff at first, so let's soften it. Imagine you're standing in a room on a quiet evening. The lights are low, the air is still. Even though you can't see it, the room has a temperature. Not just in one corner, but everywhere. Near the floor, near the ceiling, by the window. If you were able to measure it carefully, you'd find that each point in the room has its own temperature value. Slightly warmer here, slightly cooler there. Temperature in this sense behaves like a field. It spreads across space, quietly assigning a number to every location, whether anyone is paying attention or not. Now imagine stepping outside on a breezy day. The wind isn't just here or there. It has a direction and a strength at every point around you. In one spot, it brushes lightly against your arm. A few steps away, it tugs more firmly at your jacket. The wind forms a pattern across space. That pattern is another kind of field. Physicists use the word field to describe any quantity that works like this. Something that fills space completely, without gaps. Something that exists even when nothing dramatic is happening. Something that doesn't need objects to carry it from place to place. In this way of thinking, space is never just an empty container. It's more like a canvas already covered with subtle textures, even before anything is painted on it. The idea of fields didn't begin with quantum physics. Long before anyone talked about electrons behaving strangely, scientists realized that forces like magnetism and electricity didn't quite fit into a purely object-based picture. A magnet could influence another magnet without touching it. An electric charge could affect its surroundings instantly, shaping how other charges moved nearby. To explain this, physicists introduced the idea of an invisible influence spread throughout space. Instead of one object reaching out to another across emptiness, space itself became active. Each point around a magnet or an electric charge carried information about how it would affect something placed there. That information was the field. What's important here is that the field doesn't belong only to the object that creates it. Once it exists, it becomes part of the environment. You can step into it, move through it, feel its effects. The field is not a message being sent. It is the condition of space itself. As physics progressed, this idea became more powerful and more general. Eventually, scientists began to wonder whether fields weren't just a convenient way to describe forces, but something more fundamental. Perhaps fields weren't created by particles. Perhaps particles emerged from fields. This is where the story begins to shift more decisively. In the modern picture, the universe is not made of particles moving through empty space. Instead, it is made of fields that exist everywhere, all the time. The electron field fills the entire universe. The field associated with light fills the entire universe. Other fields, less familiar but just as real, do the same. Even in the most distant, seemingly empty regions of space, these fields are still there. Quiet, calm, unexcited, but present. This changes how we imagine nothing. Empty space is no longer a blank stage waiting for actors to arrive. It is already rich with structure, already full in a subtle way. When nothing is happening, the fields are simply resting, like a calm sea before any waves appear. At this point, it's tempting to imagine fields as physical substances like invisible fluids or fabrics. Those metaphors can be helpful at first, but they can also mislead us if we cling to them too tightly. Fields are not made of stuff in the usual sense. They don't have tiny pieces of their own. They don't pile up in corners or leak out through cracks. A field is better thought of as a rule that applies everywhere. A quiet instruction written into the universe, telling each point in space how it is allowed to behave. When nothing disturbs the field, it stays in its most relaxed state. When something interacts with it, the field responds. It can bend, ripple, vibrate, or shift. And those responses are what we eventually come to recognize as physical phenomena. This way of thinking requires a small adjustment in how we picture reality. Instead of starting with objects and asking how they interact, we start with fields and ask how patterns arise within them. Instead of imagining particles traveling through space, we imagine space already filled with something capable of motion. It's a quieter picture, less cluttered, less crowded with little dots zipping around, but it's also deeper. It gives us a single background that can explain a wide variety of behaviours without switching stories halfway through. For now, it's enough to hold on to one simple idea. A field is something that exists everywhere, assigning possibilities to space itself. It doesn't need particles to justify its existence. It doesn't turn off when no one is looking. It is the calm presence that makes activity possible. As we rest with this idea, it begins to feel less abstract and more familiar. After all, we live surrounded by things we can't see but constantly experience. Air pressure, temperature, sound. Even silence has a quality shaped by the space it fills. In the same way, fields quietly shape the universe, even when nothing obvious is happening. And as this picture becomes more comfortable, we're ready to take the next gentle step. To explore how these ever-present fields behave when we look at them closely, especially when we look at them on the smallest scales imaginable. That's where things become quantum, and where the calm background begins to shimmer. Now that the idea of a field has gently entered the picture, it's worth taking a little time to let it become familiar. Not in the sense of memorizing a definition, but in the quieter sense of letting an image settle. Fields can sound abstract when introduced in textbooks, but when approached slowly, they turn out to be one of the most intuitive ideas in modern physics. To do that, we'll deliberately stay away from equations and symbols, not because they're wrong or unimportant, but because tonight they would only distract from the feeling of the idea itself. Instead, we'll let images do the work. Imagine a large, perfectly calm lake at dawn. The surface is smooth, almost glass-like. There are no waves, no ripples, no boats passing by. At first glance, it might seem like nothing is happening, but the lake is still very much there. It has depth. It has tension across its surface. It has the ability to respond if something disturbs it. That calm lake is a useful way to think about a field in its resting state. The field exists everywhere across the surface, even when nothing draws attention to it. The absence of waves does not mean the absence of water. It simply means the water is not being excited into motion at that moment. Now imagine tossing a small pebble into the lake. A ripple forms. It spreads outward, creating a circular pattern that moves across the surface. The ripple is visible. It has shape, it has energy, but it is not something separate from the lake. It is the lake, moving in a particular way for a short time. When the ripple fades, nothing essential has left the lake. The water remains, the field remains. This image is helpful because it allows us to imagine activity without objects. The ripple is real, but it is not a thing you could scoop up and carry away. It's a temporary pattern, dependent on the presence of something deeper and more continuous. Fields in physics behave in a similar way. They are not collections of tiny pieces. They are continuous backgrounds that can be disturbed, shaped, and set into motion. When they are undisturbed, they rest quietly. When something interacts with them, patterns appear. Another image that can help is that of a stretched fabric, laid flat and smooth. The fabric itself fills the space completely. There are no gaps. If you press gently in one place, the fabric dips. If you pluck it, vibrations travel outward. The dips and waves are not separate objects sitting on the fabric. They are the fabric responding to being touched. In this way, a field is not something added to space. It is something that defines how space behaves. This is an important shift. In everyday thinking, we imagine space first and then imagine things placed inside it. Fields ask us to reverse that order. Space is not an empty container waiting to be filled. It is already permeated by fields that give it structure and character. This idea helps explain why fields do not have edges. A field does not suddenly stop at a boundary, like a wall or a box. It extends smoothly from one region to the next. Its values may change, its behaviour may shift, but it does not abruptly end. This continuity is one of the reasons fields are so useful in physics. They allow nature to behave smoothly, even when the outcomes we observe appear discrete or sudden. It's also worth noticing how fields remove the need for constant motion. In the particle picture, everything seems busy all the time. Tiny objects racing through empty space, colliding, bouncing, exchanging energy. In the field picture, much of reality is calm by default. Motion becomes the exception, not the rule. A field can exist quietly, doing nothing in particular until something disturbs it. This gives the universe a kind of built-in stillness, a baseline of rest. This stillness is not emptiness, it is more like a held breath, full of potential but not yet expressed. One of the most comforting aspects of this picture is that it does not require constant activity to justify existence. A field does not need to prove it is there by producing particles. It does not vanish when nothing is happening. It simply remains everywhere, assigning gentle possibilities to each point in space. This also helps explain why fields can overlap without interfering with one another in obvious ways. Just as temperature and wind can coexist in the same room, multiple fields can occupy the same space at the same time. Each one contributes its own quiet layer of influence. Each one responds in its own way when disturbed. You are sitting, right now, in a place where many fields overlap. Fields associated with matter, with light, with forces that hold atoms together. You don't feel them individually. You experience their combined effect as solidity, warmth, and presence. None of this requires you to imagine invisible machinery or complex inner workings. The beauty of the field picture is that it replaces mechanical stories with atmospheric ones. It invites you to think in terms of environments rather than components. A field is an environment that exists everywhere. When something happens, it happens within that environment. When nothing happens, the environment does not disappear. It simply rests. As we become comfortable with this idea, something subtle shifts in how the universe feels. It becomes less like a collection of isolated events, and more like a continuous landscape. A place where change emerges from stillness, and where activity fades naturally back into calm. This perspective prepares us for the next gentle step in our journey. Because fields, as we've described them so far, behave in smooth and familiar ways. They rise and fall, they spread and settle. But when we look closely enough, especially at the smaller scales, we discover that fields have a more delicate structure. Their calm is not perfectly smooth. Their vibrations are not infinitely divisible. Instead, they move in careful steps, like notes on a scale rather than a continuous slide. That is where the word quantum begins to quietly matter. And with that thought resting softly in the background, we can let this image of calm, continuous fields linger for a moment longer before allowing it to take on its next layer of subtlety. With those images of calm lakes and stretched fabric still gently in mind, we can take another unhurried step, because a single field on its own is only part of the story. The deeper picture that modern physics paints is quieter still, but also richer. It suggests that the universe is not built on one background, but on many layers of fields, all existing together, everywhere. It can help to imagine this not as a crowded space, but as a layered one. Think about standing in a quiet room. Even if nothing seems to be happening, several invisible layers are already present. There is temperature, quietly different near the window than near the door. There is air pressure, gently pressing on your skin. There may be a faint hum of sound, even if you're not consciously aware of it. None of these cancel each other out. They overlap, each contributing something subtle to the overall experience. Fields in physics behave in much the same way. There isn't just one field filling the universe, there are many. Each one has its own character, its own way of responding when disturbed, its own kind of motion. Some fields are associated with what we usually call matter. Others are associated with light. Others still are linked to the forces that quietly hold everything together. Crucially, these fields do not compete for space. They do not push one another aside. They coexist, layered perfectly on top of each other, each present at every point in space at the same time. This can feel strange at first, because our everyday intuition is built around objects that exclude one another. Two solid things cannot occupy the same place at the same time, but fields are not solid things. They are more like conditions or possibilities assigned to space itself, and many conditions can exist together without conflict. In this picture, the electron field fills the entire universe, not just around atoms, not just near Earth, everywhere. Even in the vast emptiness between galaxies, the electron field is still there, resting quietly. The same is true of the field associated with light, and of other fields that are less familiar but just as fundamental. Most of the time, these fields are calm. They are in their resting states, not producing anything that would draw attention. This is why the universe often feels empty, not because nothing is there, but because nothing is being emphasized. When a field is disturbed, when energy enters it in just the right way, it can respond by forming a localized pattern, a ripple, a vibration, a temporary knot of activity. That pattern is what we observe as a particle. Seen this way, particles are not the occupants of space. They are the events that occur within fields. This helps explain something quietly remarkable. No matter where you go in the universe, an electron behaves exactly the same way. It has the same mass, the same charge, the same response to its environment. There are no slightly heavier electrons hiding in distant galaxies. No worn-out ones drifting through ancient stars. In an object-based picture, this perfect sameness would be astonishing. How could countless separate objects created at different times and places be exact copies of one another? In a field-based picture, it becomes natural. Every electron is not a separate thing. Every electron is the same type of ripple in the same underlying field. Their sameness is not a coincidence. It is a direct consequence of their shared origin. This layered field picture also changes how we think about space itself. Space is no longer an empty box in which fields sit. Instead, space is the arena where fields already exist. The fields give space its physical meaning. Without them, space would be an abstract idea with nothing to happen in it. And this brings us to a particularly calming realization. Even when the universe appears quiet, it is never truly bare. The fields remain, patient, present, ready to respond but under no obligation to do so. There is no switch that turns them off. This means that what we often call empty space is not a void, but a kind of deep background hum. A resting configuration of many overlapping fields, each one quietly defining how reality could behave if disturbed. It also means that the universe is not constantly busy at its core. Most of the time, nothing dramatic is happening at all. The fields are simply there, existing without effort, without urgency. This can be a surprisingly comforting thought. Reality does not depend on constant activity to sustain itself. It does not flicker in and out of existence, it rests. When something does happen, when light appears, when matter forms, when interactions occur, it happens locally, briefly, and then fades back into the background. The fields do not disappear when the event is over. They return to calm. In this sense, the universe is less like a machine with moving parts and more like a landscape where weather occasionally passes through. Storms form, waves rise, patterns appear, and then, inevitably, things settle again. As we grow more comfortable with this layered picture, we can begin to appreciate how much explanatory power it has. It unifies sameness and difference. It explains why particles behave consistently without needing individual identities. It gives us a way to talk about emptiness without invoking nothingness. Most importantly for our slow journey tonight, it gives us a universe that is gentle at its foundation. A universe whose default state is quiet presence, not frantic motion. In the next step of our exploration, we'll begin to look more closely at what happens when these fields are disturbed at very small scales. We'll discover that their vibrations are not infinitely smooth, but carefully structured, that their motion comes in subtle steps, like notes rather than slides. But for now, it's enough to rest with this image. A universe woven from many overlapping fields, all present everywhere, all usually calm. A universe where what we call matter is not something added to space, but something that briefly happens within it. Up to this point, fields have felt calm, continuous, and almost classical, like smooth surfaces or gentle backgrounds that respond gracefully when disturbed. And for many everyday situations, that picture works beautifully. But when we begin to look more closely, when we listen more carefully to what fields are doing at very small scales, something delicate and surprising begins to emerge. The calm background is still there. The fields still fill space, but their motion is no longer infinitely smooth. This is where the word quantum quietly enters the story. In everyday life, we're used to smooth change. You can turn a dimmer switch and gradually brighten a room. You can slowly pour water into a glass, raising the level millimetre by millimetre. Between any two values, there's always something in between. Change feels continuous, but nature, at its deepest level, often prefers steps. A helpful way to imagine this is with music. On a violin string, you can slide your finger smoothly and produce a continuous change in pitch. But on a piano, each key produces a specific note. You can't play the note halfway between two keys. You move in discrete steps, from one allowed sound to the next. Fields, when examined closely enough, behave more like the piano than the violin. When physicists say a field is quantized, they don't mean it suddenly becomes digital or mechanical. They mean that the ways it can vibrate are limited to specific patterns. Not any motion is allowed, only certain rhythms fit. Think again of the calm lake. In everyday experience, you might imagine that you could create a ripple of any size you like, as small or as gentle as you wish. But at the deepest level, fields resist this idea. Their excitations come in smallest possible portions. You don't get infinitely tiny ripples. You get the smallest whisper the field is capable of making, and then multiples of that. This smallest whisper is not described with numbers tonight. We don't need formulas or symbols. It's enough to understand it as the field's natural unit of motion. The simplest way the field can be disturbed. When a field is excited in exactly one of these smallest units, we observe what we call a particle. This is an important moment in the story, because it means that particles are not added to the field from the outside. They are what the field does when it vibrates in its most minimal, allowed way. In this sense, a particle is not a thing sitting on top of the field. It is the field, expressing itself briefly and locally. This also explains why particles appear in discrete amounts. Light, for example, does not arrive as a continuous drizzle of energy. It arrives in individual taps. Each tap corresponds to the field vibrating in one of its smallest allowed patterns. The field cannot half vibrate in that way. It either does or it does not. At first, this stepped behaviour can feel artificial, almost like a limitation, but it turns out to be deeply stabilising. It prevents energy from leaking away into infinitely small disturbances. It gives structure to motion. It allows patterns to persist. Another quiet change comes with this quantum picture. Probability becomes unavoidable. When fields vibrate in these smallest patterns, they do not point to exact locations in the way solid objects do. A vibration can be spread out. It can overlap with itself. It can exist as a range of possibilities rather than a single point. This is not because we are ignorant. It is because the field itself is not localized in a sharp object-like way. A useful image here is fog. You can see that the fog is present. You can see where it is thicker and where it thins. But asking for the exact position of the fog doesn't quite make sense. It is inherently spread out. In the same way, a quantum excitation of a field has regions where it is more likely to be noticed, and regions where it fades gently away. Its presence is real, but its boundaries are soft. This is why attempts to force quantum particles into behaving like classical objects always feel awkward. The discomfort is not in the mathematics, it is in the mental picture. We are asking patterns to behave like pebbles. Once we let go of that expectation, much of the strangeness fades. The quantum behaviour of fields also introduces a subtle kind of restlessness. Even when a field is in its calmest possible state, when no particles are present, it is not perfectly still. It cannot be. The rules that govern its motion prevent absolute silence. Instead, the field gently trembles. Not enough to form full particles, but enough to ensure that perfect stillness is never reached. This trembling is not noise, it is structure. A quiet reminder that the field is alive with possibility, even when nothing obvious is happening. Importantly, this does not mean the universe is chaotic at its core. Quite the opposite. The quantum behaviour of fields is governed by precise rules. The allowed vibrations are well defined. The probabilities follow consistent patterns. The apparent softness comes from depth, not from disorder. And once again, we don't need to name those rules explicitly tonight. We don't need constant symbols or equations. We only need the feeling of the idea. Fields are calm backgrounds, but their calm has texture. Their silence has grain. They do not respond in infinitely small ways. They respond in the smallest ways they are allowed to. This realization completes a quiet transformation. What began as a universe of tiny objects has become a universe of ever-present fields, and what began as smooth, continuous backgrounds has become a landscape of gentle, quantized motion. Particles, in this picture, are no longer mysterious intruders. They are expected, natural, the simplest songs the fields know how to sing. As we move forward, we'll begin to look more closely at these songs, at how different fields produce different kinds of particles, at why some are heavy and others are light, at how these patterns interact, influence one another, and sometimes briefly come into existence only to fade again. But for now, it's enough to sit with this image, a universe where nothing is perfectly still, but nothing is frantic either, where motion comes in careful steps, where activity emerges from calm in the smallest, most controlled ways possible, a universe that moves not with a roar, but with a quiet rhythm, steady, structured, and deeply restful to contemplate. As fields take on this quantum character, something else quietly steps into the story, not as an add-on and not as a complication, but as a natural companion to everything we've already seen. That something is probability. In everyday life, probability often feels like a measure of uncertainty, a sign that we don't have enough information. If you flip a coin, you say there's a chance it will land heads or tails, not because the coin itself is confused, but because you haven't tracked every tiny detail of the motion. In principle, if you knew everything, the exact force of the flip, the air resistance, the angle, you might imagine predicting the outcome perfectly. For a long time, scientists hoped the same would be true at the deepest level of nature. That probability in physics was simply a placeholder for missing knowledge, that particles really did have exact positions and motions, and we just hadn't learned how to see them clearly enough. But quantum fields tell a different story. In the field-based picture, probability is not a temporary crutch. It is part of how reality behaves. The field itself does not assign sharp, single-point answers to questions like, where is this excitation? Instead, it offers a spread of possibilities, a pattern of likelihood across space. This is not because something is hidden. It is because the excitation itself is spread out. Think back to the image of fog drifting through a valley. You can say the fog is present. You can see where it thickens and where it thins, but asking for the exact location of the fog misses the point. The fog does not occupy one precise spot. It occupies a region, with gentle gradients rather than sharp edges. Quantum excitations of fields behave in a similar way. They are real, but they are not point-like in the classical sense. They have shapes, they have extents, they fade gradually rather than stopping abruptly. When physicists talk about probability in this context, they are not saying, we don't know where the particle is. They're saying, this is how the field expresses its presence. Probability becomes a description of the field structure, not a confession of ignorance. This shift can be surprisingly calming once it sinks in. It removes the tension of trying to imagine invisible objects darting around unpredictably. Instead, we imagine patterns that are naturally spread out, gently weighted towards some regions more than others. In this picture, asking where a particle is becomes more like asking where a sound is loudest in a room. The sound is everywhere, but it has peaks and valleys. Some places are more intense, others are quieter. The sound does not need to collapse into a single point to be real. The same is true for quantum fields. This probabilistic structure also explains why measurement plays such an important role in quantum physics. When a field excitation interacts with something large, like a detector, a screen, or even an atom, it doesn't suddenly become an object because we looked at it. Instead, the interaction forces the field to express itself in a specific way at a specific place. The spread-out pattern meets a local interaction, and a particular outcome emerges. This can feel dramatic when described in technical language, but at heart it's quite gentle. It's simply the field responding to its environment, a continuous background encountering a localized influence. Importantly, this does not mean that reality depends on human observation. Fields do not wait for us to look before they exist. They do not need consciousness to decide what to do. They interact with everything around them constantly, whether or not anyone is paying attention. What measurement really means in this softer picture is interaction. When a field interacts strongly with something else, its possibilities narrow into a particular event. Another comforting aspect of probability in quantum fields is that it follows consistent patterns. These patterns are not random in a chaotic sense. They are highly structured. If you repeat the same situation many times, the overall distribution of outcomes remains stable and predictable. This is why quantum physics, despite its reputation for weirdness, is one of the most accurate frameworks science has ever produced. Its probabilistic predictions are precise, reliable, and astonishingly well tested. The unpredictability lies in individual events, not in the overall behaviour. This again fits beautifully with the idea of fields as the foundation. A field is not concerned with single outcomes. It defines a landscape of possibilities. When events occur, they are selections from that landscape, shaped by interactions and constraints. Seen this way, probability feels less like a flaw and more like a feature of a deeply flexible reality. A reality that allows multiple possibilities to coexist until something nudges one of them into expression. There is also a subtle connection between probability and rest. A field in its calmest state still contains potential. It still carries the full range of ways it could respond. Probability describes that readiness, the quiet tension of what might happen without requiring anything to happen at all. This is why even empty space filled only with resting fields is not truly inert. The probabilities are still there. The possibilities still hum softly in the background. At no point does the universe need to roll dice. There is no cosmic randomness being thrown around carelessly. Instead, there is a gentle unfolding of allowed patterns, guided by the structure of the fields themselves. As we sit with this idea, it becomes clear that probability in quantum physics is not an intrusion into an otherwise orderly world. It is a reflection of a deeper order, one that is richer and more accommodating than rigid determinism. It allows reality to be stable without being frozen, predictable without being mechanical, calm without being lifeless, and perhaps most importantly for us tonight, it allows us to listen without tension. There's nothing to catch, nothing to pin down. The picture works even if it stays a little soft around the edges. In the next part of our journey, we'll look more closely at what happens when fields settle into their calmest possible configurations, what physicists often call the vacuum, not as emptiness, but as rest. But for now, it's enough to notice that probability is not something layered on top of quantum fields. It is woven into their very nature, a quiet guide describing how patterns of reality gently choose where to appear. As probability settles into the picture, it naturally leads us toward a quieter question. If fields can vibrate, ripple, and express themselves as particles, what happens when they are not doing any of those things? What does a field look like when it is completely at rest? At first, this may sound like an odd question. In everyday life, rest often feels like absence. If a room is quiet, nothing is happening. If a lake has no waves, we might casually describe it as empty or inactive. It's easy to assume that rest means nothingness, but fields invite us to think more carefully. Imagine again that calm lake at dawn. The surface is smooth, no ripples catch the light, no boats disturb the water. From a distance, it might seem like there is nothing to see, but of course, the lake has not disappeared. The water is still there, filling every part of the basin. Its surface tension remains, its depth remains, its ability to respond remains. The lake is not gone, it is resting. A field behaves in much the same way. When physicists talk about a field at rest, they mean the field in its calmest possible condition, the state where it is not vibrating in any of its allowed patterns, where no particles are present, where no energy is being actively exchanged. This calm condition has a name in physics, but tonight we can think of it simply as the field's resting state. What's important is this. The resting state of a field is not the same as the absence of a field. The field still fills space. It still assigns possibilities to every location. It still exists everywhere, quietly, without drawing attention to itself. This distinction is subtle, but deeply important. because it means that even when we remove all particles from a region of space, we have not removed everything. The fields remain, the background remains. The stage, if you like, is still fully built, even if no actors are currently performing. This is why modern physics no longer treats empty space as truly empty. What we casually call vacuum is not nothingness. It is a state of rest, a moment when the fields are not excited into visible activity. But even rest in the quantum world has texture. Earlier, we touched on the idea that quantum fields can never be perfectly still. Their rules prevent absolute silence. Even in their calmest state, there is a gentle, unavoidable trembling. Not enough to form particles that persist, but enough to ensure that the field is never completely inert. This trembling is not noise, it is not chaos. It is a consequence of the field being a dynamic entity rather than a static object. A quiet reminder that the field is alive with possibility, even when it appears calm. You can think of it like the faint motion you feel when standing on solid ground. The earth feels stable beneath your feet, but it is constantly vibrating with tiny movements, tectonic shifts, thermal motion, distant waves. Stability does not require absolute stillness. In the same way, the resting state of a field is stable but not frozen. This has a profound implication. It means that the universe does not need to be filled with particles to exist meaningfully. Long stretches of cosmic space, far from stars and galaxies, are not barren voids. They are regions where fields are simply resting. They are quiet, not empty. This picture also reshapes how we think about energy. In everyday language, energy is often associated with motion, heat, light, or work being done. But in the field picture, energy also has a baseline, a lowest possible level corresponding to rest. That baseline is not zero in the sense of non-existence. It is zero in the sense of no further calm being possible. Again, we don't need to talk about numbers or formulas here. We don't need to mention constants or symbols. It's enough to understand that the field has a natural resting point. A calm configuration it prefers when left undisturbed. From this calm, everything else emerges. When energy enters the field, it cannot do so arbitrarily. It must follow the allowed patterns. It must excite the field into one of its quantized vibrations. And those vibrations appear to us as particles, interactions, and forces. Seen this way, the vacuum is not a backdrop behind reality. It is reality in its most relaxed form. This idea can feel surprisingly peaceful. It suggests that the universe, at its foundation, is not a frantic place filled with constant activity. Its default state is rest. Activity is the exception, not the rule. Particles flicker into existence, interact, and fade away. Fields remain. This also helps explain why the universe is so remarkably stable. If reality were built from tiny objects constantly colliding in empty space, one might expect chaos. But if reality is built from fields that prefer calm and only respond when disturbed, stability becomes natural. The universe is not holding itself together through constant effort. It is resting, with occasional moments of expression. And perhaps most comforting of all, this resting background does not depend on us. It does not need observation. It does not need meaning assigned to it. It simply is. Long before stars formed, the fields were there. Long after galaxies fade, the fields will remain. Their calm is not fragile. It is fundamental. As you listen, you might notice how this idea changes the emotional tone of physics. It shifts the story from one of relentless motion to one of quiet endurance. From a universe constantly doing things to a universe content to be, most of the time. In the next part of our journey, we'll begin to explore how different fields give rise to different kinds of particles, how a ripple in one field feels like light, while a ripple in another feels like matter, and how these patterns interact, shaping the world we experience. But for now, it's enough to rest with this image. A universe filled with fields that do not vanish when nothing happens. A vacuum that is not empty but peaceful. A background that holds everything quietly without effort. After spending time with the idea of resting fields, a natural curiosity begins to surface. If fields are always there, calm and present even when nothing seems to be happening, then what exactly are the things we usually call particles? What is an electron or a photon really made of in this quieter picture of reality? The answer modern physics offers is surprisingly gentle. A particle is not a tiny bead. It is not a dot moving through space like a grain of sand through air. Instead, a particle is a localized vibration in a field, a ripple, a brief structured movement in something that already exists everywhere. Returning once more to the image of a calm lake can help here. When the surface is perfectly still, the lake is present but quiet. When a stone touches the surface, a ripple appears. That ripple has a location. You can point to where it is strongest. You can watch it move outward, but it is not separate from the lake. It does not exist independently. It is simply the lake behaving differently for a moment. In the same way, when a field is disturbed in just the right way, a localized pattern forms. That pattern carries energy. It can move. It can interact. It can even be detected by instruments, and that is what we call a particle. This reframes existence itself in a subtle but important way. Instead of thinking of particles as things that exist on their own, we begin to think of them as events, something that happens rather than something that permanently is. An electron in this picture is the electron field vibrating in one of its allowed patterns. A photon is the light field doing the same. They are not ingredients added to the universe. They are expressions of what the universe is already made of. This also explains why particles can appear and disappear without breaking any deep rules. When a ripple fades on a lake, nothing has been destroyed. The water remains. When a particle vanishes, the field does not vanish with it. The field simply returns to a calmer state. Nothing fundamental is lost. This way of thinking can feel unfamiliar at first, because we are so used to identifying reality with objects. Chairs feel solid. Tables feel fixed. Even our own bodies feel like stable things. But when physics looks closely, it finds that stability itself is an illusion created by countless ongoing processes. At the deepest level, nothing truly stands still. Particles persist not because they are frozen objects, but because the patterns that create them are stable. They are rhythms that the field knows how to maintain for a while. Some patterns last only an instant. Others can endure for billions of years, but all of them are patterns nonetheless. This is why describing a particle as a ripple is not poetic exaggeration. It is a precise shift in perspective. The particle is not riding on the field, it is the field, momentarily shaped. This perspective also helps dissolve a long-standing mystery. Why do particles sometimes behave like waves and sometimes like points? In the field picture, this is no longer strange. A ripple naturally spreads, it naturally overlaps. But when it interacts locally, it can deposit energy at a specific place, just as a wave can gently tap a buoy even while spreading across the water. The wave-like and particle-like aspects are not two separate behaviours stitched together. They are two ways of noticing the same underlying process. Another quiet consequence of this view is that particles lose their individuality. An electron does not carry a personal identity. It does not have a history written into it as an object. It is simply a manifestation of the electron field behaving in a particular way at a particular time. If another electron appears somewhere else, it is not a copy. It is the same kind of ripple, arising from the same underlying field. This is why electrons are perfectly identical, down to every measurable detail. They are not manufactured items that need to be matched. They are the same process repeating itself. This realization often produces a soft moment of wonder. The sameness we observe in nature is not enforced from the outside. It arises naturally from the fact that there is one field everywhere, expressing itself again and again. In this sense, the universe is economical. It does not build reality from countless individual components. It builds it from a small set of ever-present fields, capable of producing a vast variety of patterns. Matter, then, becomes a kind of choreography. Fields move, fields interact, patterns form, persist, and dissolve. What we call a thing is simply a stable dance that lasts long enough for us to name it. This view also removes the need to imagine particles travelling through empty space like tiny bullets. Instead, we imagine activity shifting across a continuous background. When a particle moves, it is not a bead flying forward. It is the field's pattern changing from one region to another, like a ripple passing across water. This makes motion itself feel gentler, less mechanical, less violent. Nothing is being hurled through nothingness. The field is simply reconfiguring itself over time, and because fields fill all of space, there is no sharp boundary where a particle begins or ends. There are regions where the pattern is strong and regions where it fades. This softness is not a flaw. It is a faithful reflection of what the field is doing. By the time we reach this point in the story, the universe has quietly transformed. What once looked like a collection of tiny solid objects has become a living tapestry of patterns. What once felt like emptiness has become a calm, supportive background. And what once seemed like strange, contradictory behaviour has become the natural outcome of a deeper, simpler structure. Particles are not the foundation of reality. They are the moments when reality expresses itself in a way we can notice. And as we continue, this understanding will help us see interactions and forces in a new light as well, not as pushes and pulls between objects, but as conversations between fields, gentle influences spreading through an ever-present background. For now, it's enough to rest with this idea. A particle is not a thing you could hold. It is a ripple, a pattern, a brief emphasis in a field that never goes away. Once we begin to see particles as ripples in fields rather than tiny independent objects, a long-standing mystery in physics quietly dissolves. It is a mystery so familiar that we often stop noticing how strange it really is. Every electron in the universe is exactly the same, not almost the same, not similar within a margin of error, exactly the same in every measurable way. Each one carries the same charge, the same mass, the same response to light and forces. An electron formed near the beginning of the universe behaves no differently from one produced moments ago in a laboratory on Earth. This perfect sameness is so complete that physicists do not label electrons individually. There is no electron A or electron B in any meaningful sense. There is only an electron wherever and whenever it appears. In an object-based picture of reality, this is deeply puzzling. If electrons were tiny objects, like grains of sand, we would expect at least some variation. Objects are usually shaped by their history, where they came from, how they were formed, what they have interacted with along the way. Two rocks are never perfectly identical. Even coins minted from the same machine show tiny differences if you look closely enough. So why would nature produce countless particles that are flawless copies of one another? In the field picture, the answer is almost effortless. There is only one electron field. Not one here and another one there, not separate fields attached to separate electrons. One field filling all of space, everywhere in the universe. When an electron appears, it is not a new object being manufactured. It is the electron field vibrating in one of its allowed patterns, right where conditions allow that vibration to form. Every electron is the same kind of ripple, because it is a ripple of the same underlying field. This is similar to the way waves behave on water. No matter where you create a ripple, near the shore, in the middle of the lake, or far out at sea, the ripple follows the same rules. Its shape, speed, and behavior depend on the properties of the water, not on some identity attached to the ripple itself. You do not need to label ripples to tell them apart. They are not individuals, they are expressions of the same medium. In this sense, electrons have no personal identity. They do not carry tags or serial numbers. They do not remember where they have been. They are not distinguishable in principle, not just in practice. This idea can feel strangely impersonal at first, but it also has a quiet elegance to it. Nature does not keep track of countless tiny objects. It relies on a small number of ever-present fields, each capable of expressing itself in consistent ways. Sameness is not enforced, it emerges naturally. This also explains why physicists can swap electrons in equations without changing anything about the outcome. The universe does not care which electron is which, because there is no meaningful distinction to be made. All that matters is that the electron field is excited here or there, now or then. Once you accept this, many familiar statements take on a deeper meaning. When we say an electron moves from one place to another, we're not tracking a tiny bead travelling through space. We're describing how a pattern in the electron field shifts over time. The field's excitation fades in one region and grows in another, smoothly transferring energy and influence. There is continuity, but not individuality. This also sheds light on a subtle but important point. If electrons are not individual objects, then the universe is not built from a collection of tiny personal entities. It is built from shared structures, common backgrounds, reusable patterns. Reality, at its deepest level, is communal. The same is true for other particles as well. Photons are excitations of the field associated with light. Quarks arise from their own fields. Each particle type corresponds to a particular field, and each field gives rise to its own characteristic patterns. This is why different particles have different properties, not because they are made of different stuff in the usual sense, but because different fields behave differently when they vibrate. Some fields produce patterns that interact strongly with others. Some produce patterns that barely interact at all. Some give rise to stable structures that can persist for long periods. Others produce fleeting events that vanish almost as soon as they appear. But within each category, sameness reigns. This view also brings a quiet sense of order to the universe. The rules are not written separately for each particle. They are written once into the behavior of the field. Everything else follows. There is a subtle wow hidden here, but it is not the kind that demands excitement. It is the kind that invites stillness. The universe achieves complexity not by stacking countless unique pieces, but by allowing a few simple ingredients to express themselves again and again. In this picture, identity becomes a property of patterns, not of things. What matters is not which particle, but what kind of excitation. Not who, but how. This may feel abstract, but its consequences are everywhere. The chemistry that allows molecules to form, the electricity that powers devices, the light that reaches your eyes. All of it depends on the perfect sameness of these field-based patterns. If electrons were even slightly different from one another, the universe would be wildly unpredictable. Atoms would not form reliably, matter would not be stable. Life, as we know it, would be impossible. The calm regularity of the world around us is not an accident. It is a reflection of the deep uniformity of the fields beneath it. And yet, This uniformity does not lead to monotony. From the same electron field arise countless different arrangements: atoms, molecules, solids, liquids, living cells, thoughts, complexity built on sameness. As we rest with this idea, it becomes clear that the field picture does not strip the universe of richness. It explains how richness is possible at all. In the next step of our journey, we will take this insight one step further. If particles are not objects but patterns, then they are not static. They are ongoing processes, things that continue to happen rather than things that simply sit there. Reality, it turns out, may be better described with verbs than with nouns. By the time we arrive here, the idea that particles are not tiny objects but patterns in fields has had time to settle, and once it does, another quiet shift becomes almost inevitable. If a particle is a pattern, then it is not something that simply exists, it is something that continues to happen. This is a subtle distinction, but it changes how we think about reality at a deep level. In everyday language, objects feel static. A chair sits in a room, a stone rests on the ground. Even when nothing seems to be happening, the object appears to persist unchanged. It is easy to imagine that at the deepest level, reality is built from things that simply are. But the field picture gently undermines this intuition. A ripple on a lake does not exist in the same way a rock does. It exists only as long as the motion continues. The moment the water stops moving in that particular pattern, the ripple is gone. Nothing has been destroyed, but the event has ended. Particles, in the field-based view, are much closer to ripples than to rocks. An electron is not a static entity sitting quietly in space. It is an ongoing excitation of the electron field. As long as that excitation persists, we say the electron exists. When the excitation fades or transforms, the electron is no longer there. This does not mean particles are fragile or fleeting in the everyday sense. Some excitations are extraordinarily stable. They can persist for vast stretches of time, but their persistence is active, not passive. It is maintained by the structure of the field and the rules that govern its behaviour. In other words, nothing truly stands still. Even when a particle appears motionless, its existence is sustained by continual activity at the level of the field. The pattern holds its shape not because it is frozen, but because the conditions allow it to keep happening in the same way moment after moment. This is similar to a flame burning steadily on a candle. The flame looks stable. Its shape seems constant, but it is not the same flame from one instant to the next. Fuel is consumed. Heat flows, chemical reactions proceed. The flame persists precisely because it is a process, not an object. Particles are like that, stable patterns maintained by ongoing dynamics. This way of thinking also softens our relationship with time. If particles are processes, then time is not something that merely happens to them from the outside. Time is part of what they are. A particle is something that unfolds. This helps explain why motion is so deeply woven into the fabric of reality. In a world built from static objects, motion would need to be added as an extra feature. In a world built from processes, motion is the default. Matter becomes motion held in shape. That phrase can sound poetic, but it is also precise. The shape comes from the allowed patterns of the field. The motion comes from the fact that the field is dynamic. The combination produces something that can look solid, stable, and object-like at human scales. At deeper scales, however, solidity dissolves into activity. This perspective also changes how we think about interactions. When two particles interact, it is not two objects colliding like billiard balls. It is two patterns overlapping, influencing one another through the shared background of their fields. The interaction is a process affecting processes. Energy flows, patterns adjust. Some excitations fade, others emerge. Nothing needs to be pushed or pulled in the mechanical sense. The fields respond to one another according to their rules, and what we observe is the visible result of that response. This process-based view also removes the need for sharp boundaries. Objects in everyday life have edges. You can draw a line around them. You can say where they end and where something else begins. But field excitations are not so neatly contained. Their influence fades gradually. Their presence blends into the background. This is why quantum particles resist being boxed into precise locations. It is not that they are trying to evade measurement. It is that they are not the kind of thing that has rigid edges to begin with. They are activities, not containers. Once this sinks in, it becomes easier to understand why reality often feels softer and more relational at its deepest levels. Things exist not in isolation, but through their ongoing participation in a larger pattern. This does not make the world less real. It makes it more alive. A universe built from processes is a universe that is always, quietly, in motion. Not frantic motion, not chaotic motion, but the steady, lawful unfolding of patterns that know how to sustain themselves. It is also a universe that does not need to carry a vast inventory of objects from one moment to the next. It only needs to carry the fields and their rules. Everything else can arise as needed. This economy is one of the most beautiful aspects of the field picture. With a small set of ingredients, it produces a staggering range of phenomena. Light, matter, forces, and even the structures that make life possible all emerge from the same underlying processes. Seen this way, reality feels less like a warehouse of things and more like a piece of music. Notes arise, combine, resonate, and fade. The music persists not because individual notes are permanent, but because the structure allows new notes to keep appearing. Particles are notes in the universe's music. They do not need to be stored. They do not need to be tracked individually. They arise when conditions allow, and they fade when conditions change. This perspective also invites a gentler emotional response to the idea of impermanence. If everything is process, then change is not a failure of stability. It is the natural way stability is expressed. The universe does not cling to forms. It allows patterns to emerge, do their work, and dissolve back into the background. As we prepare to move forward, this understanding will be crucial, because once particles are seen as processes, interactions become easier to understand. Forces no longer need to be mysterious pulls across empty space. They become ways in which fields influence one another's ongoing activity. Conversations rather than collisions. But for now, it's enough to rest with this idea. Matter is not a collection of frozen things. It is motion, held in recognizable shapes by the quiet rules of fields. Reality is less noun than verb, and in that steady unfolding, there is a calm that remains, even as everything continues to happen. Once particles are understood as processes rather than objects, interactions begin to look very different. The familiar image of tiny things pushing, pulling, or colliding with one another starts to feel less helpful. Instead, a quieter picture takes its place, one where interactions are not impacts between objects, but responses between fields. In everyday experience, forces feel direct. You push a door and it moves. You pull a rope and something follows. It's natural to imagine that deep down, forces work the same way. That one object somehow reaches out and tugs on another across space. But fields invite a gentler explanation. Imagine standing near a campfire on a cool night. You feel warmth on your skin, even though nothing is touching you. The fire does not throw tiny pieces of heat at your body. Instead, it changes the conditions of the surrounding space. The air carries energy. Your skin responds. The interaction happens through a shared environment. This is much closer to how forces work in a field-based universe. When two particles interact, they are not exchanging invisible punches. They are patterns in fields responding to one another through the fields they share. One field shifts slightly, and another responds. Influence spreads smoothly, not abruptly. Take light as an example. Light is not a stream of glowing pellets fired across space. It is a vibration of the field associated with light itself. When this vibration encounters matter, another set of fields, it does not crash into it like a projectile. Instead, the fields overlap. They interact. Energy and momentum are redistributed according to the rules they both obey. What we observe as absorption, reflection, or emission is simply the outcome of that interaction. This same idea applies to electric charge. When one charged particle affects another, it does not reach across emptiness to grab it. The field associated with electric influence is already present everywhere. A charged particle alters that field locally. Another charged particle responds to the altered field where it happens to be. Nothing travels instantaneously from one particle to the other. The interaction unfolds through the shared background at a finite pace, guided by the structure of the fields involved. This removes the need for action at a distance, a concept that once troubled even the greatest physicists. In a field-based picture, nothing acts across empty space. Space is never empty. The fields are already there, carrying influence naturally. This perspective also makes interactions feel less violent. Instead of imagining particles smashing together, we imagine patterns overlapping and adjusting, a conversation rather than a collision. One field says, in effect, "This is how I'm configured here." Another field responds, "Then this is how I will adjust myself." The result may look dramatic at human scales: sparks, light, heat, motion, but underneath, the process is smooth and continuous. This also explains why interactions depend so strongly on context. A particle does not carry all its behavior inside itself like a sealed package. How it behaves depends on the fields around it. Change the environment, and the interaction changes. In this way, particles are not isolated actors. They are participants in a shared system. This relational view is deeply woven into modern physics. The properties we assign to particles, such as charge or mass, are not standalone traits. They describe how a particle's field interacts with other fields. They are relational properties, not intrinsic labels. Even mass, which feels like the most object-like property of all, fits this picture. Mass determines how a field responds to motion and influence. It shapes how patterns persist and change. It is not simply how heavy an object is, but how resistant a pattern is to being reshaped by its surroundings. Seen this way, forces become less mysterious and more conversational. They are the language fields used to negotiate with one another. This perspective also helps explain why forces can be unified in theory. If forces are not separate mechanisms but different ways fields interact, then it becomes possible to describe them using a common framework. Different fields, different rules, but the same underlying idea. Interaction is not something added to reality. It is how reality expresses its interconnectedness. There is also a calm elegance in the way influence spreads. Changes do not leap instantly across the universe. They propagate. They ripple. Just as a disturbance on a lake moves outward at a steady pace, influence in fields travels according to well-defined limits. This gives the universe a kind of rhythm. Nothing happens everywhere at once. Everything unfolds locally, moment by moment. And once again, we don't need formulas or symbols to appreciate this. We don't need to describe speeds or constants. It's enough to feel the difference between a world of objects throwing forces at one another and a world of fields quietly adjusting themselves. The latter feels softer, more coherent, more patient. As this idea settles in, interactions begin to feel less like interruptions and more like natural responses. Fields do not clash. They converse. They adapt. They find configurations that allow patterns to persist or transform. This view prepares us for the next gentle step in the story. Because once interactions are understood as field responses, the act of measurement itself begins to look different. Detection is no longer a mysterious intrusion, it becomes just another interaction, one field influencing another, bringing a pattern into focus. But for now, it's enough to rest with this image. A universe where nothing pushes across emptiness, where influence spreads through ever-present backgrounds, where forces are not invisible strings, but quiet adjustments in shared fields. Reality in this view is not a battleground of objects. It is a conversation of patterns, unfolding smoothly through a universe that is always already connected. Once interactions are understood as conversations between fields, the idea of measurement begins to feel much less mysterious. Measurement is often described as one of the strangest aspects of quantum physics, but much of that strangeness comes from imagining particles as tiny objects that suddenly change their behaviour when someone looks at them. In the field-based picture, nothing so dramatic is required. Measurement is not a magical act. It is not a special moment where consciousness reaches into reality and forces it to choose. Measurement is simply another interaction, a particular kind of conversation between fields, where a subtle pattern becomes localized enough for us to notice it. To see how this works, imagine again the image of sound filling a room. Music plays softly from a speaker. The sound waves spread everywhere, bouncing gently off walls, furniture, and air. The sound is real, but it is not concentrated at a single point. It exists as a pattern across the room. Now imagine placing a microphone in one spot. The microphone does not create the sound. It does not summon it into existence. It simply interacts with the sound field locally. In doing so, it converts a small portion of that spread out pattern into a definite signal, a voltage, a recording, something that can be stored and displayed. The sound has not collapsed in any dramatic sense. A particular interaction has simply pulled one aspect of it into focus. Quantum measurement works in a similar way. Before measurement, a particle-like excitation of a field may be spread out. It may exist as a range of possibilities, weighted towards some regions more than others. When it interacts with a detector, a screen, or a piece of matter, that interaction forces the field to respond locally. A specific outcome appears, not because reality was undecided, but because the interaction demands a definite exchange of energy and momentum at that location. What we call a particle appearing is really the field responding in a concrete way to a concrete interaction. This is why particles so often seem to show up when we look for them. Not because looking creates them, but because looking involves interaction. Detectors are not passive observers. They are physical systems built from fields themselves. When a field excitation encounters them, something must happen. The field expresses itself where the interaction occurs. This view removes the need for any special role for observation or awareness. Fields do not wait for attention. They respond to whatever they interact with. A rock, a detector, a cloud chamber, or a distant star all count as valid interaction partners. Measurement is just a name we give to a certain class of interactions, ones designed to produce stable, readable outcomes. This also explains why measurements feel irreversible. Once a field has transferred energy to a detector, the process involves many degrees of freedom. Heat spreads, Signals amplify, information disperses. Reversing all of that would require undoing an enormous cascade of interactions. The definiteness of measurement does not come from a sudden choice by reality. It comes from the practical irreversibility of large-scale interactions. Seen this way, the mystery softens considerably. Before interaction, a field excitation can remain spread out, maintaining its probabilistic structure. During interaction, that structure is forced to express itself locally. After interaction, the field settles into a new configuration, often calmer than before. Nothing supernatural has occurred, only fields responding to fields. This perspective also helps explain why different measurement setups produce different outcomes. The field does not carry a single, hidden answer waiting to be revealed. It carries a range of possibilities. The way those possibilities are expressed depends on how the interaction unfolds. Change the detector, and you change the conversation. The field responds differently because the context is different. This is not ambiguity, it is responsiveness. Another helpful image is that of light passing through a window. Sunlight fills a room, diffused and gentle. When it passes through a prism, colours appear. The prism does not create the colours. It reveals aspects of the light that were already there, by forcing the light to interact in a specific way. Measurement works much like that prism. It does not summon particles from nothing. It reveals how a field responds when constrained by a particular interaction. This also explains why measurement outcomes are discrete. When a detector records a click, it does not register half a click. The interaction either transfers a full unit of energy or it does not. The field's quantized nature ensures that outcomes come in steps, even if the underlying pattern was spread out beforehand. Again, no formulas are needed to appreciate this. No symbols, no sharp mathematics. Only the idea that fields have allowed ways of responding, and interactions force one of those responses to occur locally. Once this settles in, the emotional tone of quantum measurement changes. It becomes less unsettling and more intuitive. Reality is not being watched into existence, it is being engaged. The universe does not behave differently because we look at it. It behaves differently because interactions happen. This is an important distinction, especially in a quiet exploration like this one. It allows us to understand quantum behavior without assigning it drama or mystery beyond what is actually there. The mystery becomes a gentle one, a reflection of depth rather than confusion. As we move forward, this understanding will help us approach even more abstract ideas with calm. Concepts like symmetry, conservation, and order will begin to feel less like imposed rules and more like natural consequences of how fields interact and respond. But for now, it's enough to rest with this image. Measurement is not creation, it is revelation through interaction. A moment when a field, already present and already structured, is asked a question by another field and answers in the only way it can. After spending time with interactions and measurement, another idea begins to surface naturally. It is not something added on top of fields, but something that seems to guide them quietly from within. This idea is symmetry. The word symmetry can sound technical or even intimidating, but at its heart it is remarkably simple. Symmetry is not about equations or abstract symbols. It is about balance, about sameness under change, about the idea that some things remain constant even when you look at them from different angles or in different situations. We encounter symmetry all the time, often without noticing it. Think of a smooth, round bowl. You can rotate it slightly and it still looks the same. Turn it a little more and again, nothing essential changes. The bowl has a kind of quiet agreement with rotation. It does not care which way you face it. Its form remains stable. Or think of a calm snowfall. Each snowflake may be unique, but the overall pattern of falling snow feels uniform. The rules governing how snow falls do not depend on where you are standing or which direction you are facing. The process is balanced, repeatable, and consistent. In physics, symmetry captures this idea at a deeper level. It describes situations where the underlying rules do not change, even when circumstances do. One of the most important symmetries in nature is the idea that the laws of physics are the same everywhere. An experiment performed here on Earth will behave the same way if performed far away in another galaxy. There is no preferred location written into the universe, no special place where the rules suddenly shift. This sameness is not enforced by particles carrying instructions with them. It arises because the fields themselves are symmetric. They do not change their character from place to place. They fill space evenly without bias or preference. Another quiet symmetry is that the rules of physics do not depend on the direction you face. Left, right, forward, backward, the outcomes remain the same. The fields do not have a hidden orientation etched into them. They respond the same way regardless of how you turn. These symmetries feel almost obvious, but they are deeply powerful. They explain why the universe is predictable enough for science to work at all. If the rules changed from moment to moment or place to place, patterns could not persist. Stability would be impossible. What's remarkable is that symmetry is not something imposed on fields from the outside. It is built into their nature. The fields behave the way they do because certain transformations leave them unchanged. And from these quiet invariances, much of the structure of physics emerges. For example, the idea that energy is conserved, that it does not simply vanish or appear from nowhere, is connected to the fact that the laws of physics do not change over time. The field rules today are the same as they were yesterday. That temporal balance leads naturally to conservation. Again, we don't need formulas or symbols to appreciate this. It's enough to feel the idea. When the background rules are steady, some quantities remain steady too. Symmetry also helps explain why certain fields exist at all, and why they have the properties they do. Fields are not arbitrary inventions. They are the simplest structures that respect the symmetries of the universe. They are the patterns that fit comfortably within the quiet balances nature allows. This is why modern physics often feels like it is guided by symmetry rather than by guesswork. Instead of asking, what particles should we invent next? Physicists ask, what kinds of fields are allowed if the universe is to remain balanced in this way? In this sense, symmetry acts like a gentle editor. It does not dictate every detail, but it constrains what is possible. It narrows the options, guiding the structure of reality toward coherence. Symmetry also brings a sense of elegance to the field picture. The universe does not need a long list of separate rules for each situation. A small number of balance principles can give rise to a wide variety of behaviors. When symmetry is present, patterns repeat reliably. When symmetry is broken, slightly, gently, new structures can emerge. This breaking is not violent or chaotic. It is more like a preference appearing, a choice among many equivalent possibilities. Think of a perfectly round hilltop. A ball placed at the very top has no preferred direction to roll. Every direction is equivalent. But the moment the ball begins to move, one direction becomes special, not because the hill demanded it, but because the situation has shifted. In the same way, when symmetries are subtly broken in fields, particles acquire different properties, forces differentiate, structures form, complexity arises, not in spite of symmetry, but because of it. This is one of the most quietly beautiful ideas in physics. Order does not come from rigid control, it comes from balanced freedom, from rules that allow many possibilities but shape them gently. In the field picture, Symmetry is not an abstract mathematical ornament. It is the reason the universe feels consistent. It is why electrons behave the same way everywhere, why interactions follow predictable patterns, why reality does not unravel into randomness. And importantly for our slow journey tonight, symmetry is not something we need to calculate. We can feel it intuitively. It is the sense that the universe does not play favourites, that it offers the same possibilities again and again wherever you look. As we let this idea settle, it prepares us for an even deeper reflection. If fields fill space and follow quiet rules of balance, then what we call empty space may be far richer than we once imagined. Not a void, but a structured calm shaped by symmetry and possibility. That thought will carry us gently into the next part of our exploration, where nothingness itself begins to look different. But for now, it's enough to rest with symmetry as a quiet presence, not loud, not demanding, just a steady background agreement that allows the universe to be understandable at all. After spending time with symmetry and the quiet rules that guide fields, we arrive at a place that once seemed simple, but now feels very different. Empty space. The idea of nothing. In everyday language, empty space sounds like absence. A room with no furniture, a box with nothing inside, a pause where nothing happens. It feels natural to imagine the universe as mostly empty, with matter sprinkled here and there like dust in a vast void. But the field picture gently asks us to reconsider that image. In modern physics, what we call empty space is not the absence of everything. It is the calmest possible state of all the fields that fill the universe. Not a void, but a resting condition. Not nothing, but quiet. Imagine entering a large, dimly lit hall late at night. No one is speaking, no music is playing. At first it feels empty, but as you pause, you begin to notice subtle things. The air still presses against your skin. A faint hum of distant electricity lingers. The building itself creaks softly as it cools. The hall is not empty, it is simply still. Empty space, in the field picture, is like that hall. The fields are still there. They have not gone anywhere. They are simply not being excited into the kinds of patterns we recognize as particles. This is why physicists speak of the vacuum not as nothingness, but as a state, a particular configuration of fields, the lowest energy condition they can settle into. Again, we don't need numbers or formulas here. We don't need to talk about precise values or constants. It's enough to understand that every field has a preferred calm, a way of being when left undisturbed. And remarkably, even this calm is not perfectly silent. Earlier, we touched on the idea that quantum fields cannot be completely still. Their rules do not allow absolute quiet. Even in their resting state, there is a gentle, unavoidable trembling. Not enough to form lasting particles, but enough to ensure that perfect emptiness is never achieved. A helpful image here is breathing. When someone is deeply asleep, their body appears still, but breathing continues, slow, subtle, rhythmic. The stillness is real, but it is alive. It has texture. The vacuum is like that. A deep, quiet background with a faint intrinsic motion. Not agitation, not chaos, just the soft presence of possibility. This idea can feel surprising, especially if we've been taught that energy only exists where things happen. But in the field picture, energy has a baseline, a lowest level associated with rest. The vacuum is not energy free, it is energy at rest. This does not mean empty space is dangerous or unstable. Quite the opposite. It is extraordinarily stable. It is the ground state toward which fields naturally return. It is the universe's default condition. This perspective also changes how we think about cosmic emptiness. The vast spaces between galaxies are not barren deserts where reality thins out. They are regions where fields are resting, undisturbed for immense stretches of time. Particles appear occasionally, light passes through, but most of the time the fields remain calm. There is something profoundly peaceful about this image. The universe is not constantly busy at its foundation. It does not require continuous activity to sustain itself. It rests. This also helps explain why particles can appear and disappear without violating any deep principles. When a particle emerges from the vacuum, nothing has come from nothing. The field has simply shifted briefly from its resting state into an excited one, then back again, like a wave rising briefly on a calm sea. The sea does not need to be replenished when the wave fades. The water remains, the field remains. This view also dissolves a common fear associated with the idea of nothingness. Empty space is not a threat to existence. It is the condition that allows existence to be well defined in the first place. It is the quiet background that supports all structure. Without a stable vacuum, particles could not have consistent properties. Interactions would be unpredictable. Reality would lack coherence. The calmness of empty space is not trivial. It is foundational. As you listen, it may be helpful to let go of the word empty altogether, at least emotionally. Instead, think of space as filled with rest, with potential held gently in place, with fields that do not demand attention but never vanish. This perspective also prepares us for a deeper question, one that physicists are still exploring carefully. If fields fill space, and if space is defined by the presence and behavior of fields, then what exactly is space itself? Is it a container that fields occupy, or is it something that emerges from the field's relationships? That question does not need to be answered definitively tonight. It is enough to let it hover softly at the edge of our thoughts. For now, we can rest with a simpler realization. Empty space is not nothing. It is the universe in its most relaxed form, a state of quiet balance, shaped by symmetry and possibility. In that stillness, everything we observe is already waiting, not as objects, but as patterns that can arise when conditions invite them to do so. And as we prepare to take one last gentle step deeper toward the idea that space and time themselves may be part of this unfolding, it's worth pausing here, letting the calm of the vacuum settle in, letting the idea of a resting universe replace the image of a vast empty void. Because sometimes the most important thing physics can tell us is not how much is happening, but how much is quietly, patiently there. After spending time with the idea that empty space is not truly empty, another question begins to arise naturally, almost without effort. If fields fill space everywhere, and if what we call the vacuum is simply the calmer state of these fields, then what exactly is space itself? And what about time, the quiet flow that seems to carry everything along? These are not questions that demand firm answers tonight. They're invitations, gentle suggestions that the picture we've been building may extend even further than we first imagined. In everyday thinking, space and time feel like the ultimate background. Space is the stage where events happen. Time is the river that carries them forward. They feel fixed, given, and unquestionable. Fields, particles, and interactions all seem to exist within them. But as physics has looked more closely, that order has begun to feel less certain. If every physical process we observe is described in terms of fields that carry energy, influence, and structure, then space begins to look less like a container and more like a relationship. The fields do not simply sit inside space. They define how distance, direction, and connection are experienced. A helpful way to think about this is with a familiar object, a map. A map does not exist independently of what it represents. The meaning of distance on a map depends on the scale, the projection, the rules used to translate a curved surface into flat paper. Change the rules, and the sense of space changes too. In a similar way, the space we experience may be shaped by the way fields relate to one another. Distance may not be an absolute backdrop, but a measure of how strongly or weakly fields are connected across regions. From this perspective, space is not something fields live in. It is something that emerges from how fields are arranged and how they interact. Time, too, begins to soften. At the level of everyday life, time feels like a steady flow. One moment follows another. Causes precede effects. But in the field picture, time is closely tied to change, to processes unfolding, to patterns evolving. If nothing changed, time would have nothing to mark. This suggests that time may not be a universal clock ticking independently of everything else. Instead, it may arise from the way fields move from one configuration to another, from the ordering of events rather than from an external stream. Think again of music. The sense of time in a piece of music does not come from a separate clock hovering above the orchestra. It comes from the sequence of notes, from rhythm and change. Without notes, there is no music. Without change, there is no time to feel. In this way, time may be something we experience because fields are dynamic, because processes occur, because patterns form, persist and fade. This does not mean time is an illusion. It means time may be relational rather than fundamental, a way of describing change rather than a substance flowing on its own. These ideas are still being explored carefully in physics. There is no single, settled picture, and that is perfectly fine. The goal tonight is not to resolve the deepest mysteries of space and time, but to notice how naturally these questions arise once we adopt a field-based view of reality. If particles are patterns, and interactions are conversations, then space and time may be the grammar of those conversations. Not objects themselves, but structures that emerge from the relationships between fields. This layered view of reality is both humbling and calming. It suggests that what we experience is not built on rigid foundations, but on flexible, responsive structures. Structures that adapt, evolve, and yet remain remarkably stable. Reality in this picture is not a stack of fixed layers. It is a network of relationships, unfolding gently. For our purposes here, it's important to hold these ideas lightly. We do not need to imagine space dissolving beneath our feet or time slipping away. At human scales, space and time behave reliably. They are excellent approximations. They guide our lives without surprise. But beneath that reliability, there may be a deeper softness, a sense in which space and time are not the ultimate stage, but part of the performance itself. This realization adds a final layer of quiet wonder to the field picture. Not a dramatic twist, but a gentle opening. The universe becomes less like a rigid machine, and more like an evolving conversation, where even the background participates. As we approach the close of our journey, this thought allows everything we've discussed to settle into a coherent whole. Fields give rise to particles. Particles interact as processes. Interactions shape patterns. And from these patterns, the very notions of space and time may arise. Nothing needs to be forced. Nothing needs to be concluded definitively. It is enough to sense the direction of the idea. We're not standing outside the universe, watching it unfold. We are within it, patterns among patterns, participating in the same fields that shape stars, light, and empty space itself. And with that gentle realization, we are ready to let the exploration soften into reflection, to step back from explanation and allow the picture we've built to simply be present. As our journey gently comes to rest, it can help to bring everything back to where it began, not with distant stars or abstract ideas, but with you, here, listening, Because the picture we've been slowly building is not just a description of the universe far away, it is also a description of where you are right now. If fields fill all of space, then they fill the space you occupy as well. Not metaphorically, literally. The air around you is not empty. Beneath the air, beneath the walls and the floor, beneath the planet itself, fields are quietly present. Fields associated with matter, with light, with forces that hold atoms together and allow patterns to persist. You're not sitting inside emptiness. You're resting within a layered continuous background of fields, and you're not separate from them. Your body is not a collection of tiny objects glued together. It is a complex, stable pattern formed from ongoing processes, fields interacting with fields, excitations held in shape by quiet rules. The atoms that make up your body are not fixed building blocks. They're activities that have learned how to persist together for a while. Even your thoughts, as fleeting and private as they feel, arise from physical processes, patterns of electrical and chemical activity, fields interacting in delicate, coordinated ways. Nothing about this makes thought less meaningful. If anything, it makes it more remarkable. Meaning arises not from permanence, but from pattern. In this view, you are not a thing placed into the universe. You're something the universe is doing here, now. A local expression of the same fields that give rise to light, matter, and space itself. This can feel strangely comforting. There is no sharp boundary where the universe ends and you begin. There is continuity, a gradual shift from one pattern to another. You're part of the same fabric, shaped by the same quiet principles, participating in the same ongoing conversation. Earlier we spoke about particles as ripples, processes, and events. The same language applies here. Your existence is not a static fact. It is an unfolding, a process sustained moment by moment. Stable, but alive. And like all processes, it rests when it can. The universe, at its foundation, prefers calm. Fields return to rest when disturbances fade. The vacuum is a state of balance. Activity is meaningful precisely because it emerges from stillness and eventually dissolves back into it. There is a gentle rhythm here, not a race, not a struggle, a rhythm of emergence and return. This rhythm is reflected everywhere, in breathing, in waves rising and falling, in thoughts appearing and drifting away, in nights giving way to mornings, and mornings easing back into night. When we imagine the universe as a pile of objects, it can feel crowded and restless. When we imagine it as a sea of fields, it feels more spacious, more forgiving. There is room for things to arise, to change, and to pass without needing to be held tightly. This does not make reality fragile. It makes it resilient. Patterns can form and dissolve without threatening the background that supports them. Loss does not mean annihilation. Change does not mean collapse. The fields remain. This perspective also invites a softer relationship with uncertainty. Not everything needs to be pinned down. Not everything needs sharp edges. Reality works even when it remains a little blurred at the boundaries. Probability in this view is not a failure of knowledge. It is a reflection of openness, of multiple possibilities coexisting until interaction calls one of them into expression. And when something does become definite, when a particle appears, when a measurement registers, when a moment crystallizes, it does so gently, through interaction, not decree. Nothing is forced. As this understanding settles, the universe begins to feel less like a puzzle to be solved, and more like a landscape to be inhabited. You don't need to master it. You don't need to control it. You're already part of it. Fields do not judge. They do not hurry. They respond. And in that response, everything we experience takes shape. So tonight, as you rest, you can imagine yourself not as a small object in a vast emptiness, but as a pattern within a larger calm, supported, surrounded, held in place by quiet rules that have been working reliably for billions of years. The same fields that allow stars to shine also allow your body to rest. The same principles that shape light and matter also shape the gentle fading of thoughts as sleep approaches. Nothing special needs to happen now. The universe does not need your attention to continue being itself. It has been doing so long before this moment, and it will continue long after. You can let your thoughts drift, knowing that even drifting is just another pattern, rising and falling within a steady background. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or you're already floating somewhere between waking and dreaming, thank you for being part of this quiet journey. If you'd like to join again for more gentle wanderings through science and the universe, you're always welcome. The fields are still here, the calm remains, and in this moment, there is nothing you need to do but rest. Sleep peacefully, wherever and however you may be.